Welcome back to another video. So in this video, we'll be looking at differentiability and analyticity of functions defined on the complex plane. So let's look at a definition real quick. So this is going to be, most of this content will reflect on material you've seen in Calc 1. So um, let's go over what a derivative means in complex functions, in terms of complex functions. So let f of z be a complex function. Okay. Then, so f prime of z, this is defined to be the following. So the limit as delta z approaches 0 of f of z plus delta z minus f of z divided by delta z. Okay? And this is provided that the limit exists. Okay? Provided that the limit exists. So this definition really remarks back to calculus 1 in looking at the definition of the derivative, right? But in 2 dimensions, you're looking at the limit of slopes of secant lines, right? So this definition just reflects off on the calculus 1 definition of the derivative, right? Right, so reflects off on that definition, okay? So to use this definition to evaluate derivatives of functions, it's pretty straightforward. So find f prime of z where f of z equals to z squared plus 3 times z. All right. So this is just a polynomial, a complex polynomial, right? With powers of z and different coefficients, complex coefficients, right? So this is a polynomial, complex polynomial. Okay. So to figure out f prime of z, so you would expect it would be 2z plus 3, right? So let's see. Okay. So the limit as delta z goes to 0 of f of z plus delta z minus f of z divided by delta z. Okay. So this equals to the limit as delta z goes to 0 of z plus delta z squared. Okay. Minus 3 times z plus delta z. Okay, that's f of z plus delta z minus, minus z squared minus 3z. All that divided by a delta z. Okay, all divided by delta z. And so from this point forward, you're just simplifying the quantity inside the limit, right? So this would equal to the limit as delta z goes to 0 of, so the numerator would be z squared, and we will have a plus 2z delta z plus delta z squared. So that would be this quantity here. And that would be, the second term would be minus 3z minus 3 times delta z. Minus z squared plus 3 times z over z squared, right? Delta z, not z squared. What am I thinking? Sorry about that. Delta z, right? So we should see terms cancel, like the z squares. Z squared minus z squared is 0, so they will cancel. The 3 z's will cancel, right? And we will have this expression. The limit as delta z goes to 0 of 2z delta z plus delta z squared minus 3 times delta z divided by delta z. Now, each one of these terms in the numerator have a delta z in it, right? So we can factor out a delta z in each term, right? So we'll have a delta z over delta z. And then we'll have a 2z plus delta z minus 3. Okay. The delta z's will cancel from the top and the bottom. And this will equal to the limit as delta z goes to 0 of 2z plus delta z minus 3. And this should equal to 2z minus 3. Exactly what we would expect. Okay. Right, just based on the power rule for derivatives in Calc 1, we should get 2z plus minus 3. 2z minus 3, and this is what we have here. Okay, so pretty straightforward to computing the derivative using the definition, right? So the next portion is I'm going to write out some differentiation rules. And these will be the same as the differentiation rules you've seen in Calc 1, right? So if I take the derivative with respect to z of a constant, this will always be 0, right? For any constant c, okay? The second, if I have a constant times a complex function, f, so this equals to c times f prime of z, okay? Third rule, the derivative of a sum or a difference of two complex functions, this would equal to the sum and or difference of the derivatives, right? d dz of f of z plus g of z is equal to f prime of z plus or minus g of z, g prime of z, excuse me. The fourth rule is the product rule will apply for complex functions. So if I have a product of two complex functions and if I want to differentiate those, well, this would equal to f prime of z times g of z plus f of z times g prime of z. Okay, g prime of z. The quotient rule would still apply, right? F of z over g of z. This will equal to g of z times f prime of z minus f of z times g prime of z divided by g of z squared. That's the quotient rule for derivatives. That'll still apply, right? And that's just the chain rule. So if I have a composition of two functions, and if I want to differentiate it, this will equal to f prime of g of z times g prime of z, right? The chain rule still applies. And then if I want to take a derivative of a power on z, this refers back to the power rule for derivatives in Calc 1. Okay, so those are the differentiation rules that are similar you've seen in Calc 1, right? So these rules right here. Okay, so let's actually see how these are viewed in a specific example. So, or examples. Okay. All we do here is just find the derivatives. of the following functions. So if I have one function like this, z squared over sit z plus 5. And then the other function, once you try out, is this one, f of z is equal to I z squared plus 4z cubed. All right. So try to work on these examples and let's see what you came up with. So I'll give you some time to work on these. Okay. All right. So I assume you worked on these examples. Let's actually work out the solution for these. Okay. So this one, we're going to use the quotient rule. The quotient rule here, right? Figure out f prime of z. So f prime of z, this equals to low times d high, the derivative of the numerator, which is 2z, minus high, the numerator function, times the derivative of the denominator function. So in this case is 6, divided by the denominator function squared. All that squared. Okay, so this equals to, so f prime of z, this would equal to, we'll have 12z squared plus 10z minus 6z squared over 6z plus 5 squared. And this would equal to, I'm going to leave the denominator like this. And the numerator is just 6z squared plus 10z, right? So this here is the derivative of that function, right? Okay. Part B is looking at this function here, right? So this time we're going to use the chain rule. Chain rule here, okay? So f prime of z, this would equal to 3 times, well, iz squared plus 4z squared times the derivative of the inside function, which in this case is iz squared plus 4z. So this will be times 2iz plus 4. So this right here is the derivative. Okay. So hopefully that made sense. All right. So a derivative exists as long as, if we go back up just a few inches, or yeah, we scroll back up. So we can define a derivative as long as this limit exists, right? That's going to be important. Okay, that's the important fact. So there's going to be often times where we would have to show if a function does not have a derivative, right? So here's an example of one such function, right? Show that f of z is equal to z bar, z conjugate is nowhere differentiable. Nowhere differentiable. Okay. And all we have to do is show that this limit as delta z goes to 0 of f of z plus delta z minus f of z divided by delta z does not exist, right? It does not exist. Let me write that a little bit clearly. D N E does not exist. Okay. So try to think about this example and see how we would show this. Okay. I guess you've looked at this for a few minutes. In order for in order to show if a limit does not exist in the complex plane, well, we would choose two we would choose two paths, okay? And we would show that the limit of this quantity here does not exist. So they'll reach two different values, right? So let z equal to x plus iy, and let's say delta z equals to delta x plus I times delta y. Okay, these are just two numbers. Okay, so um, so this quantity f of z so this quantity inside this limit, this would equal to z plus delta z conjugate, conjugate minus z conjugate divided by delta z, right? And so this equals to, so by the addition of conjugates, this is the same as delta z plus delta z conjugate minus delta z minus z conjugate divided by delta z. And so we would arrive at this quantity here. So delta z divided by delta z conjugate divided by delta z. Okay. So in terms of the real and imaginary components, so in terms of the delta x and delta y, okay, so we're looking at this quantity. Okay, so we just reduced it down to that. So next, all we have to do is choose our two paths to look at. So if I look at the first path being, so if I choose any random point on the complex plane Z, so one path could be if I approach Z along the horizontal, right? So what that would constitute is let delta y equal to 0 and delta z equal to delta x. Oh, shoot. So we're approaching the horizontal, okay? And then the second path, we can do the same idea, but we're going to approach it along the vertical, right? So like that. So in this case, we're going to let delta x be 0. And delta y equal delta z, excuse me, delta z equal to delta y, right? So we're going to evaluate the limit of this quantity by using those two paths, okay? So along the first path, so this would equal, so this limit would equal to this limit. Delta z goes to 0. The delta y is 0, so delta x divided by delta x. So this is 1. However, on the second path, we're letting delta x be 0. So that will reduce down to this quantity. The limit is at delta z goes to 0 of minus I delta y divided by I times delta y, which is a minus 1. So these numbers do not equal, right? So those approach to different values, right? So therefore, by the two path test. So the limit does not exist since we have two values that don't equal each other on two different paths. Okay, since the limit does not exist, well, clearly there's no derivative at any z point in the complex plane. So there's no derivative for f of z equals z bar. Okay, so hopefully that made sense. Okay, so now we're gonna get into what is called we're gonna get into a separate set of complex functions, and those are what are called analytic functions. Okay, analytic functions. All right. So a complex function, w equals f of z, is analytic at a point z naught if f is differentiable at z naught and every point in some neighborhood of z naught. So this is what it means to be analytic. Take a look at the definition of this, of what an analytic function is and what a differentiable function is. So analytic is sort of a much more powerful terminology of what it's a much more refined definition of how a function would behave at z naught. Okay, so essentially we're going to look at points in some disk. It could be an epsilon neighborhood, right, which contains z naught. And we're going to look at if the function is analytic at every point inside this epsilon neighborhood of z naught. If it is, then it's analytic. Okay. Okay, so we're looking at differentiability of functions that may be defined in some circle that's centered at z naught. Okay. F of z is analytic in a domain D if f of z is analytic at every point in D. All right. So they also call this holomorphic. That's another way to describe these type of functions, holomorphic or analytic or sometimes regular. But throughout the textbook, they call complex functions being analytic if it's differentiable at z naught and an open neighbor and at some neighborhood of z naught. Okay. So also a function is a function that is analytic on every point in the complex plane is what's called an entire function. So if you have a function that is analytic at every point in the complex plane, it's what's called an entire function. Okay. So for example, every polynomial, complex polynomial written out in this form, an times z to the n plus a to the n minus 1 times z to the n minus 1. Okay, plus all the way down to a1z plus a0. Every complex polynomial is an entire function. Okay. All right. Another example is a rational function. A complex rational function, mind you, right? Where P and Q are polynomials, right? So P of Z and Q of Z are complex polynomials. So I shouldn't say that, it's analytic. Entire means it's everywhere analytic. So a rational function is analytic except at z naught, some points z naught where q of z naught is 0. Okay. All right. So those are the conditions for when a rational function is analytic, right? And it really depends on looking at the domain of your function, right? So mostly you'll look at rational functions, and we don't want to have division by 0, right? 0 plus 0i in this case. So figure out where those points would cause that to happen, and just say that, well, your function's analytic except at those set points that you found. Okay. So so in this case, so in this case, z naught, points z naught are called singular points. So they're called singular points. Much further down in this course, we're going to be getting, we're going to talk about different types of zeros for a complex function, right? They can be a removable singularity, they're isolated singularities, there's poles. It gets pretty crazy when looking at the zeros of a complex number, the zeros or undefined values in terms of complex functions. Okay, so I'll do another example here. So another example of this. So if I have this function, f of z is equal to 4 times z divided by z squared plus 2z plus 2, right? You can use the quadratic formula to figure out the roots of the polynomial in the denominator. So you'll get 1 plus I and then 1 minus I. So you can really say that this function is discontinuous at z is equal to 1 plus I and z equals to 1 minus I, right? Okay, so these points right here and here, these are singular points. Singular points. So there, it's not even defined, right? So there won't be a derivative at the points 1 plus I and 1 minus I. Okay, so those are what are called singular points. Okay, and also another thing to take note here is that if I have two functions that are analytic, f of z and then g of z, so if they are analytic, then so are the sum or difference is analytic. The product is analytic, just use the product rule, and then the quotient, right? They're analytic functions themselves. So for the rational function in particular, you have to find out where, so singular values. Z naught where g of z naught is 0, right? So we have to figure out those singular points there too. Okay. Last but not least, what I want to go over that you've seen in Calc 1 is L'Hopital's rule. L'Hopital's rule. And this reflects on how the rate of change for two functions is sort of coinciding with one another, right? And so this is the rule. Z approaches z naught of f of z divided by g of z. This would equal to the limit as z approaches z naught of f prime of z divided by g prime of z if f of z naught is 0, g of z naught is 0, and g prime of z naught is not 0. Okay? Pretty much what you expect in L'Hopital's rule, right? So you have an indefinite form, right? 0 over 0 or plus or minus infinity over infinity, right? Those are the indeterminate forms. And so if you have those forms, you can use L'Hopital's rule to compute the limit of a rational function, right? So for example, if I have so I want to use L'Hopital's rule to find this limit. So the limit as z approaches I of z to the 7th plus I divided by z to the 4th minus 1. Or I'm z to the 14th plus 1. Plus 1. Z to the 14th plus 1. Okay, this is the example. All right. Take a few minutes to work on this example. Okay. And while I drink my soda. Okay. So I assume you worked on this example, right? If you plug in z equals I into this quantity here, so we'll have I to the 7th plus I over I to the 14th plus 1. I to the 14th plus 1, right? To figure out whether we have an I or a minus I or a 1 or a minus 1, we just take the exponent number, we divide it by 4, and we look at its remainder. So for example, if I take 7 divided by 4, I will get a remainder of 3. Okay, so in this case, we'll have a minus I plus I, not plus 1. Over I to the 14th, so 14 divided by 4, so that would be a 3 with a remainder of 2. So that would be a -1. So -1 plus 1. And what do you know? We have an indeterminate form. So we're going to apply L'Hopital's rule here, right? So that's the first step to check if you have an indeterminate form, 0 over 0 or infinity over infinity, right? So by L'Hopital's rule, this label as LH, L apostrophe H, this is equal to the limit as z approaches I of the derivative. So in this case, it's 7z to the 6th divided by 14z to the 13th by using the product rule. So this equals to the limit as z approaches I of, so we'll have 1/2 times 1 over z to the 7th, z to the 7th. And so this equals to 1/2 times 1 over I to the 7th. That would be a minus I. So minus 1/2, 1 over 2I, okay? And this would equal to minus 1/2 times I. Okay, so that is the limit there. So hopefully that made sense. Okay, so that's an introduction on derivatives, and here are these problems for you to check comprehension. So problems. Page. And as always, leave a comment if you have questions or what to improve. I am open to suggestions or questions, okay? So, hope you enjoyed this so far. So the next video, we'll look at a very special way to show that if a function is analytic, okay? So stay tuned. But other than that, hope you enjoyed this video, and I'll see you in the next one. Take care.